Okay, so this is a slab of current. Okay, so I've got current flowing down in this direction. This is like a thick sheet of paper. So this thing goes on and on forever in the Y direction and in the X direction, but it's finite in the Z direction. It's a thick plane. And my current is flowing in the X direction here in this particular picture. So make sure you understand the setup before I go through the solution. I want to find the magnetic field some distance away from that slab of current. Now, because we have an infinite slab of current, my total current is infinite. I can't even talk about I total here. I is infinite. So what we have instead is a current density that in this case will be measured in amps per square meter. Remember, J is current per cross-sectional area. Okay, so now here's the same setup, but we're looking at a cross-section of that. So this slab goes on and on in this picture forever in the Y direction and forever towards our face and into the computer screen. We're just kind of right in the middle. I want to find the magnetic field above or below, and inside, find the magnetic field inside this slab. And we're going to do it using Ampere's law. So let me try to draw this. So again, this thing goes on forever in that direction and in this direction. And my magnetic field line or my current lines are coming out at us. And J is density, current density, that's amps per square meter. This cross-sectional square meter. Okay, so the way we do this, let's do inside first. So here is my XY plane right here. I want to find, let me make sure I got my parameters right. What was my total height? B was the total height. So this right here is B over 2. And down here would be negative B over 2. And I'm going to go up a height, say Z. I want to find the magnetic field, a height Z above the XY plane inside the material. So Z is less than B over 2. Okay, I build this Amperian loop that exploits the symmetry we have. Right now we have rectangular symmetry, so I want a rectangular loop. That comes up a height Z and has length L. So I'm up here at Z. This is, if you're curious, down to negative Z. And I have to pick a direction. So I want to pick a direction that will follow where I think the magnetic field lines are going anyways. So this guy is just essentially a whole bunch of wires glued together. So if I consider just that wire right there, his magnetic field would go like this on top and like this on the bottom. So my magnetic field should go up here in the material itself, even up here outside of the material. We'll go to the left, up here above the XY plane, and to the right down here. My DL vectors, I want to go around the loop counterclockwise because I want to go in the same direction as B. So I get to choose which way I'm going around. I'm going to traverse the curve like this in the counterclockwise direction. So on each one of these segments, I'm going to have a little DL vector. There, DL points to the left. Here, DL points down. Here, DL points to the right, and here, DL points up. So I've got 4 different segments I have to think about, because each of those are different. On section 1, I'm just going to redraw this section here. I was going in that direction. B pointed in that direction. DL pointed in the same direction. B and DL were parallel. Trying to write B as parallel to DL. The dot product of parallel vectors is just the product of their magnitude. So on this section, let's call that, I think they call it C1 in some online resources. I'm just calling it circle 1. The integral just on that little section for 1 of B dot DL would just be the line integral of DL times magnitude of B. Line integral of DL was just length. How long is that? That is L long. So I get LB, magnitude of B. Now, I kind of glossed over that from the symmetry, we know B has to be constant along that line. It would make no sense whatsoever for B to be bigger right here than it is right here. Like, there's nothing special about that spot in the universe. They're both the same distance from the center. It would make no sense for B to be different values at different height, or at the same height in 2 different spots. So from a symmetry argument, we know B is constant. That's why I'm able to factor out that magnitude of B. Okay, on section 2. Section 2 points down like this. DL points down. B has 2 different parts. Up here in this top section, B is pointing to the left. Down here in the bottom section, B is pointing to the right. So B is changing across that segment of wire, but on every single part of it, B is perpendicular to DL. B points to the left or B points to the right. DL was always down. So the double or the single line integral of B dot DL will be 0 because B is perpendicular to DL and the dot product of perpendicular vectors is 0. Segment 3, DL points to the right, B points to the right. That's exactly the same thing we had up here on 1. They're parallel. So on segment 3, we get the same thing we got on 1. And then on segment 4, DL points up, but B is always perpendicular to that. So on 4, we get 0. So going all the way around the loop, adding all of those up, we get those two, 2LB. So the integral all the way around B dot DL will be 2 times the length times magnitude of B. Now, Ampere's law says that line integral should be mu naught times I enclosed. So I have to figure out what total amount of current is flowing through the area I've carved out by making that loop. And that area, this is really cool with Ampere's law. It doesn't have to be flat. Like, you can draw an Amperian loop. Say this is my Amperian loop, and I've got some current flowing through it like this. I can make that shape when I say the area I'm enclosing any shape I want, as long as this is the boundary of it. That shape could be like a bubble that sticks out behind it, because any current that flows through the front also has to flow through the back. So my shape could be like a cup, or it could be that flat area in front. As long as this is the boundary, it doesn't matter what shape I put behind that. Now in this case, the most sense is just this rectangle right here. I want to figure out how much current flows through that rectangle with this curve as the boundary of the rectangle. This is where I need to use J. J is current density. I enclosed is always going to be J times your particular version of area enclosed. And when I say particular version, you have to use the units of him to figure out what he should be. If he is amps per meter, then he will be a length. If he's amps per square meter, he will be an area. These two should multiply together to give amps, because I is in amps. So J is amps. That's not area. That's amps per square meter. So I need to multiply by square meters area to get I. So J times the area, the cross-sectional area there. How big is this? Well, it's L long and it's 2Z tall. So putting these together, I get 2L magnitude of B should be J times 2ZL. The L's cancel. Oh, I always want to leave off my mu naught. Don't leave off your mu naught. The L's cancel. If the L's don't cancel, you've done goofed. My answer may depend on Z. It may depend on my distance from the center, but it should not depend on how long I chose to make my loop. I made this variable, this parameter up, and that better not appear in the answer. And it won't. It'll always cancel. The 2's also cancel. I get magnitude of B is mu naught JZ. So the magnetic field right at the middle is 0. And as we go up, we get bigger and bigger magnetic field. And similarly down here, the magnetic field, that technically this should be an absolute value of Z, because when we get down here, if Z is negative, we still have a positive magnitude for the magnetic field. Okay, that was inside. We're halfway done. Now let's do outside. Here's my slab. This distance was B over 2. So like here on the picture, we just did this line integral. Now we're going to do this one. So this is the picture I'm redrawing now. So my currents are flowing out toward my eyeballs. I'm going to draw an Amperian loop that extends out past the current that's flowing. I'm going to go around counterclockwise. We can get through this one a lot quicker. B up here flows to the left. Down here in this entire region, B flows to the right. So here, B is to the right. Here, B is to the right. Up here, B is to the left. And again, we have 4 segments. 1, 2, 3, 4. And for literally the same reasons, up on top and on bottom, B and DL are parallel. On the sides, B and DL are perpendicular. So 2 and 4, the integral of B dot DL equals 0 for 1 and 3. the integral of B dot dl. Each one will be LB, magnitude of B. So altogether, the integral all the way around of B dot dl will be those two guys, 2LB. Nothing different there. Okay. What's different is the other part. My I enclosed will be J times my area enclosed that actually contains current. My current doesn't flow all the way out. The current is only right here. The current does not go all the way to the top and the bottom. So my area enclosed will be this distance, which is B times L, not all the way out to Z, 2Z times L. So the line integral of B dot dl should be mu naught I enclosed. We get 2L magnitude of B equals J little b L. The L's cancel. I don't have a 2 over here to cancel. And I forgot my mu naught again. Mu naught over 2. That is a constant. Outside, the magnetic field is constant because this thing is basically a thick plane. And we know the magnetic field from a plane of current is constant. So that shouldn't surprise us.